Alright, 4.6, growing, gone. So, let's take a look at population here. The U.S. population in 1910 was 92 million people. In 1990, the population was 250 million. Create both a linear and exponential model of the population from 1910 to 2030, with projected data points at least every 20 years starting in 1910. Okay, now, first thing we probably want to do is start making a table, right? Now, this is kind of where it gets a little weird. And maybe not weird, but here's some hints to make it easier. I don't want to count by this many numbers, right? Okay, I really don't even want to count by that many. The way that I would like to really deal with this is think of 1910 as my 0. If 1910 is my 0, I'm going up every 20 years. So my 1 would be 1930. 1950 would be 2. You know, that's my first set of 20 years. That's kind of how you think about it. And in math, this is really like how we like to do it. It simplifies things, simplifies the process. So 1970 would be 3, 1990 would be 4, 2010 would be 5. So we go 0, 1, 2, 3, 4, 5. Much easier to deal with, right? So at 0, we had 92 million people. We'll just call it 92. And at 1990, we had 250 million, okay? And I actually forgot to go to 2030, didn't I? 6. There we go. Okay, so now we've got to figure out both a linear and an exponential model. So remember that linear and exponential mean? This is where we want to use that, okay? So let me replicate this. We'll have our orange be linear, and our exponential is going to be blue. So let's do them both here. Okay, so 0, 1, 2, 3, 4, 5, 6. And then we go with 92, 250. Okay? And then we can probably graph them on the same graph. But let's deal with this first. So, linear. To get this one, we take the last number, subtract the first number, right? 250 minus 92. Let me get out my calculator. So 158. Then we have to add once, twice, 3 times, 4 times, right? So 158 divided by 4 gives us about 39.5. So we're adding by 39.5 million people every year. Okay, that constant rate. Having the same amount of babies every year. So then we'd have 100, eraser, not pen. 131.5 here, then 171, then 210.5 million, then 250, then 289.5 millions, and then 329 millions. Okay, so there's our linear model. Alright. Now, these are really big numbers, so honestly, the best thing for us to do really is to graph it, okay? Using our graphing calculators, this is where technology comes in pretty handy. Okay, but let's do the exponential first. So for the geometric mean, 250 divided by 92 gives us 2.71739. So we're going to round 2.72. We'll round to the nearest hundredth. Okay. Now we've got to take the, let's see, we're times them once, twice, 3 times, 4 times, right? So we're going to have to take the fourth root of that number, 2.72, which I'm actually going to not round when I type it in. I'm using the number in my calculator, so it'll actually be slightly more accurate. So we take the fourth root of our answer, and we get 1.2839. So we'll say 1.284. 1.284. That's what we're multiplying by. So we're going to have to round here. So 92 times 1.284 gives us 118.5 1.128. Then we do it again. That gives us 151.676. And I'm rounding these. Then 194.752. Then 250, right? Oops. And it's slightly, it would be 0.062. And then 321.080. And then 412.266. Okay, so there's our two models. And we really, we could come up with an equation easily, right? F of x equals 92 plus 39.5x, right? And with our exponential, an equation, f of, let's actually go g of x. G of x would equal 92 times 1.284 to the x. Okay, so now in my graphing calculator, I'm going to graph that because that's going to give us our most accurate look at it. Okay, and let's compare the two. So I took those equations and I graphed them. Okay, and it would look something like this if we graphed the equation with, we'd have those points on there. Okay, so we've got the linear blue and the exponential in red. Okay, so if we're looking at that, that's our two models. Okay, that's where we see. Okay, now let's take a look at this. So this tells us what the actual population was in those years. So which model provided a better forecast for the year 2013? Okay, so let's go back and take a look at the actual data. So in 1930, so we've got 92 million here. So 1, 2, 3, 4, 5, 6. So 92, then 122.8, then 152.3, then 204.9, and then of course we had 250. Okay, so looking at those, matching them up, okay, 131, 122, 118, 122, so exponential was better, a little bit closer. 151 and 152, quite a bit closer. This one started to get way off, right? Then that one gets pretty close. Kind of a little better than that one, isn't it? And then we had 250. Okay, well let me plot those points in there and we'll see how that affects things, what that looks like on our graph. Okay, so here's another shot of what we had going on, and as you can see, this top line was our linear and the curved line was our exponential. Okay, it's pretty obvious that the exponential is modeling it much closer than the linear is. So that exponential model is better, and with population it works much better than a linear equation does, because that's how population grows. So just kind of an interesting look at both the types and how we actually do use them in real life to kind of model those situations and take a guess at what. So most likely, the model of the population being in 2013, or 2030 should be closer to 412 million. And that's an interesting question. I wonder, since we have 321, let me take a look at, see what the U.S. population was in 2010. Let's see if that matched closely. It said 309.3 million is what it was. So, yeah, getting pretty close there. Alright, we are done.